Hey there, so this is lecture 3. We're jumping around a little bit and jumping into section 2.6 on limits at infinity. So we've talked about limits at a specific point when our x is approaching a number. And now what we want to do is say, okay, that's great, but now what can we let our x go off to infinity? So positive and or negative infinity. And we can, absolutely. And it's the same kind of idea. So for the limit as x goes to infinity, we can take a look at some examples. So let's start with our polynomials, x squared plus 2x plus 3. And so now, instead of letting x go to a number, we're going to let x get really, really big. So you actually don't have to get very big to see what's going to happen here. Usually 10 or 100 is going to do it for you, or we can take a look at the graph. So if you think about, I like to just think about plugging in a big number. If I take a really big number and I plug it in here and I square it, and to that I add 2 times my big number and then subtract 3, what kind of number am I going to get? So in this case, if you think about 10, this is going to be 100 plus 20 minus 3, which is 117. If you go to 1,000, plug in 100, now you have 4 zeros plus 200 minus 3. And now you can see right away that this minus 3 is going to be really small in relation to the 200 and the 10,000. And as I get larger, even that 200 is really not big compared to the 10,000. But anyway, what we get here is 10,197, right? Getting big quickly. If I plug in 1,000, that's going to give me 1 and 6 zeros plus 2,000 minus 3. And that's going to get larger and larger and larger. So that's going to give us, let's see, 100, 1,997. There we go. And you can see this is going to get really big really quick. So this is going to go off to infinity. So our answer here is going to be positive infinity. We can also see that if we think about the graph. So this is a polynomial. So this is an x squared plus 2x minus 3 is a quadratic, and it's positive x squared. So it's going to open up. So I don't know where it's going to be, but it's going to look like this. And as we go off to infinity, if our x's go to infinity, they're going to the right. So as I trace this to the right, my answer is going up. Okay, to positive infinity. If you're going, you can also go as x goes to negative infinity. So we think about plugging in negative 10. That's going to be negative 1,000 plus 10 plus 1, all right? And that's going to give us something negative large, right? 900, subtract 10, we go to 90, 89. Right, so large. And then if you go to plug in 100, 100, that's going to give us negative 1 with 6 zeros plus 100 plus 1. And you can see how that's going to get really negatively large quickly. So this one's going to head to negative infinity. And we can see that in our graph because, again, as a cubic with that positive number, it's going to do something like this. Right? It's going to increase from right to left. So as we're going to negative infinity, which is now this direction, if we follow our graph, we're headed down, okay, to negative infinity. So you can use either at this point. So then when we get to things like 1 over x, okay, so if you think about plugging in a really big number, then let's think about plugging in 1 over 10 or 1 over 100 or 1 over 1,000, right? So this is going to be 0.1, 0.01, 0.001. And as we keep going, we're going to get 0.0001 and as many zeros as I want. So where is this going? This is getting smaller and smaller and smaller. This is headed to 0, right? And we can see that from the graph. If you think about 1 over x looks like this. Right? So as I go to infinity, it's going to head along that asymptote right there. Okay, so we're going to head to 0. What I like to do is I like to think of this as 1 over infinity when I plug it in. And infinity I like to think of as everyone in the world. And so 1 cookie divided by everyone in the world means nobody gets any cookie, right? So this turns out to be 0. That's also true in this case if we're headed to negative infinity. So this is going to be 1 over negative infinity or negative 1 over infinity. And this is going to be the same as above. So negative 0 is just 0, right? And that's because on the other side of our graph, as you're heading towards negative, you also head towards 0, okay? So whether everybody collectively owes that dollar, then do you really have to pay anything? No. Or if you have one cookie share with everyone in the world, will you get any cookie, right? Okay. So then what happens? So this is what happens if we had infinity divided by 1, right? Because there's nothing in the denominator. And this is what happens if we have 1 over infinity. But what happens if you have infinity in both places, right? So in this top number, if you plug in a really large number, you're going to square it, add it to that large number, add 1. This is going to go to infinity pretty quickly, right? It's a quadratic that goes up. X plus 2, if you take a really big number and add 2 and you continue adding really big numbers to 2, you're going to get really big numbers. So we're going to get infinity over infinity, okay? We then have to do something else, right? Because I can't divide infinities. That doesn't make sense. So let's take a look at what the graph looks like. So if I go to the graph, and let me go to my, where'd it go? There it is. We're going to plot here. Uh-oh, I don't want that. Whatever that is, take me out of that. We want, actually, almost exactly this. Let me go back to what it is. It's plus though, isn't it? Yeah, plus x plus 1. Okay, so plus x plus 1 divided by x plus 2. And let's take a look at the graph. We're looking to see what happens to the graph as x gets large. So as we're headed out this way, you can see that that's headed up, okay? So this is going to be infinity. So equals positive infinity. Now, if we go to the next one, all I did was flip it upside down, right? So that x plus 2 still goes to infinity. The one on the bottom still goes to infinity. Let's take a look at the graph. If I go up here and instead make this x plus 2 in the front, ooh, now looks what happens. As I go to infinity, you can see that that's coming down to 0. That's going to even out, get a horizontal asymptote at 0. So this one is actually going to be equal to 0 when we look at the graph. And lastly, let's take a peek at this one. So 2x squared plus 5. And what was the other part? 3x squared plus x minus 1. Oh, look what happens here. You can even see it better on this one, right? So as I go to the right, this appears to be evening out at a particular number, something like 0.6, I don't know, 0.67, 0.66, something in that ballpark, right? So this appears to be something like 0.66. Now, based on the graph, I'm going to say 0.66-ish. Because we're just guessing from the graph. But when you plug something in, those are both quadratics that are opening up. They're both going to head to positive infinity. So notice what's happening here. Let's see if I can get them all on the screen. There we go. So in 5, 6, and 7, each one of these, if I plug in a large number, I get something that looks like infinity over infinity, but I get a different answer each time. The first one I got infinity, the second one I got 0, the third one I got a non-zero number. So what we say here is that this is an indeterminate form. Okay, so infinity over infinity, ooh, just like 0 over 0, is an indeterminate form. And when that happens, what we need to do is do more work. Okay, so that we can simplify something. However, if you take a look at these, if you can see it right here in number 6, the x squared plus x plus 1 is not factorable. That's irreducible. So I'm not going to be able to factor. What's creating the infinity over infinities for these is actually this leading term, right? Because if you think about it, the plus 2 And the plus 1, that really didn't matter, right? And even this number here, when we were plugging things in up here, right? This didn't matter at all. This really didn't even matter. It was this one that was kind of driving things. So that means that leading term is what's going to drive things. So what we want to do is we want to get rid of that leading term in one or both of the places, okay? So what we're going to do is we're going to try to get rid of one of them. So my leading terms in number 5 are the x squared and the x. I want to get rid of one of them. I'm going to choose the smaller power just because I think that that's a little bit easier. So I'm going to get rid of this one. So I'm going to multiply 1 over x in the bottom of my fraction to get rid of that x. But in order to do that, I have to also do that up top. Once I do that, now I keep my limit notation because I'm not evaluating the limit. And I distribute the 1 over x. X squared times 1 over x. X over x. And I'm going to write it out once, and then I'll start skipping steps next time. And x over x plus 2 over x. Okay, distributed to each term. Then we can go ahead and reduce. So x squared over x is x over x is 1, and the 1 over x stays. In the bottom, x over x becomes 1, and then I have 2 over x. Now notice what happened. This x is now a 1, so I got rid of it. So now when I go ahead and plug in my limit, I'm going to get infinity plus 1 over infinity, and 1 plus 2 over infinity. Now this isn't technically correct mathematical writing, but we're going to let that slide. Now, what happens when you have 1 over infinity or 2 over infinity is that your one cookie share with everyone in the world. So those are both zeros. So this turns out to just be infinity plus 1 over 1, and that's just infinity, which matches what we got in our solution for number 5. So what we do here is we think about our two leading terms, and we want to multiply by 1 over the smaller of the two powers. And that's how we're going to use algebra to simplify our limits. If we take a look at number 6, we're going to do the same thing. Now remember, number 6 is the reciprocal of number 5, so the leading terms are the same. So I've got a second degree and a first degree, so I'm going to multiply top and bottom by 1 over x. When I do that, I get the limit as x goes to infinity of x over x plus 2 over x squared over x plus x over x plus 1 over x. And this is going to reduce up above the to 1 plus 2 over x plus 1 plus 1 over x. Now, if you can do this correctly, the algebraic step, without the step previous, this one right here, then that's fine. You go ahead and do that. No issues with that. Okay, from here, we're going to evaluate our limits. We're going to plug in that infinity. So this is 1 plus 2 over infinity plus 1 over infinity. Again, these two are going to go to 0. And I'm left with 1 over infinity plus 1, which is infinity. And 1 over infinity we know is 0. And so number 6 matches with what we got up above as well. And lastly, number 7. Notice here that these two have the same power in their leading terms. So I'm going to multiply top and bottom by 1 over that power. So 1 over x squared. And when we go ahead and distribute that, that becomes the limit as x goes to infinity of 2x squared over x squared plus 5 over x squared. 3x squared over x squared plus x over x squared minus 1 over x squared. Now, make sure that you simplify properly here. This is the limit as x goes to infinity. Don't lose your notation. 2x squared over x squared is just 2, plus 5 over x squared. 3x squared over x squared is 3. X over x squared is 1 over x, and 1 over x squared. Then we can go ahead and plug in our limits. Now I can drop my limit notation. This is 2 plus 5 over infinity. 3 plus 1 over infinity minus 1 over infinity. All of these fractions go to 0. And so that means my answer is 2/3, which in decimal form is 0.6 repeating. So that matches up to what we did before as well.